Hello, how are you doing?
I'm good. How are you?
Not too bad, not too bad.
Yeah, sorry about being late. Had some technical issues.
Oh, believe me, totally fine.
So I think it's the same thing as last time for the most part. Um, we added one thing, which it was just a free, like a FRQ for the practice AP exam, and that was about it.
Okay, what did we work on last time?
I'm kidding. It was a graphic. I forget what it was called. It started with a P.
Oh, polar coordinates. Okay, and then you said something about the uh AP test or ACT or something?
Yeah, we had a practice FRQ for the AP test.
Hmm, how was that?
It wasn't too bad. I got most of them. There was just one that was, um, I like switched something around. That was it.
Gotcha. Okay.
So I think I'm probably good on that.
Let's see. So I'm trying to remember what we talked about. Um, so I think we talked about kind of the basic equations that we use to convert. So we have y is equal to r sine of theta, x equals r cosine of theta, x squared y squared equals r squared, and tangent of theta equals y over x. Okay, so do you remember how did converting between rectangular and polar feel all right, or would you like to do some more practice with that?
I think I want to do more just because I don't remember
Okay,
any of it right now.
so let's say we have, this is in polar, we got -1, 2 pi over 3. What is this in rectangular coordinates?
Let's see. So I honestly don't remember.
Okay, so rectangular, man. Polar coordinates are of the form r theta,
Okay.
where you first spin an angle and then you go out a radius. And then this is your point right here. These are the equations on the right side that we use to convert. We have an r, we have a theta. What should we do?
So it would be negative cosine of 2 pi over 3 would be the x value, and then with the y value, is that how that works?
Yep. So we have y is equal to negative
Negative 1
one.
sine
Yep.
of theta,
2 pi over 3 because that's our theta.
and then the x would be negative cosine of 2 pi over 3.
Yep. Very good.
Got it. And
And
then obviously the radius is them squared and multiplied together.
yep. So we're just trying to convert to from polar coordinates to rectangular coordinates. So all we care about is if we have a y and x. So once we have x
Mm-hmm.
and y, we're done. And I forget my unit circles. I am sure 2 pi over 3 is something that you can do pretty easily, but whatever. You would get these numbers out and then put them in, parentheses like how you would normally. And that's your answer. Okay, so that looked pretty good. So let's go rectangular to polar. Let's say we're in rectangular now, and we are at x equals 3, x equals y. What is this in polar coordinates?
It would be the x would be 3 cosine of 3, and then the y would be 3 sine of 3.
This is we're in Cartesian right now,
Okay.
and we're trying to go to polar. So what we need to end up with is r theta. We're starting in xy.
Mm-hmm.
So
Okay.
we'll need to end up with r theta.
Um, I'm not sure.
Okay. So let's start with theta, because I think theta will be pretty easy. What equations do we have that have theta in them?
All of the values, like um, the properties.
Oh, you
I'm
mean the
pretty sure.
trig stuff?
Mm-hmm.
Yeah. I was just talking about in these ones.
Oh, okay.
Yeah. So
So
it's
it's
the
just the
first, second, and
x, y, and
fourth.
tan.
Yeah. But here's the thing. For these two, if we were to solve for theta, we would have r as part of our answer. but we don't know what r is yet. So, but if we look at the fourth one, theta totally depends on y and x, which is what we do have. So how can we solve for just theta using this problem?
So I guess it would be 3 sine of 3.
3 sine of 3?
Yeah, because that's the only thing. I'm not sure other than that how to do it, because it seems like you need to convert it to polar with the y value, but I don't know the formula.
Well, so let's look at tangent of theta. Tangent of theta is equal to y over x.
Okay.
Because the 3 is y and the 3 is x.
Okay.
So how do we solve for theta from here? Because we're looking for theta.
I guess you have to divide the tangent over.
But you're not going to divide tangent because tangent isn't like a number. It's what's called an operator. I don't know if you ever heard that terminology before.
Yeah,
But it's kind of like
talking about that last time.
Yeah, it's kind of like saying you want to divide over the multiplication sign.
So you have to move the theta and then move the 3 over 3 over?
Nope. So the only way you're going to be able to get rid of an operator is to do the inverse operator.
Okay.
And you'll do that to both sides. So you'll have, so these will cancel. And you have theta is equal to arctangent of 3 over 3, which is 1. And this number, so sometimes you have to be careful with canceling these because the domain of arctangent and tangent are different. So arctangent of x, or actually I'm going to say arctangent of theta, rather. Arctangent of theta. It'll only spit out answers between negative 90 and positive 90. So like on the unit circle, it'll only spit out numbers in this half. So if you have a point that's on this side, you're going to get, so say this was 135 degrees. If you do arctangent, you'll get this point right here. So
it's just like,
yeah. So if this is 135, this angle here is like about 67. So you have to double check because you actually want this angle. How you do that is you add, basically you'll take this theta and subtract the 100, so you'll do 180 degrees minus theta. Because it's like instead of going this way, you're going this way, because these angles will be the same. And also, I don't think I chose the right angle here. I don't think that's 135. I did 3 pi over 4, and whatever that number is. But we are in the right quadrant because we're in quadrant 1 here. All right, so we have our theta. Now we need to find our r. So there's 3 ways we can do that. We can do either of these and then solve for r because now we have theta. Or we can go here because we have both x and y, and then solve it like a Pythagorean problem.
I think that's probably the easiest way to do it is the Pythagorean.
Okay, so we'll take r is equal to square root of 3 squared plus 3 squared. What is that all equal to?
9.
Not 9, because it's going to be 9 plus 9, the inside, which is 18.
Wait, what? It says times.
Oh, sorry. I wrote that wrong.
Okay, I was confused for a second.
Yeah, sorry. Yep, normal Pythagorean theorem. Yep, so square root 18. Then we can separate this to be 2 times 9. And this is what we would write. We would say that our answer is 3 square root of 2 pi over 4. All right, let's do one more of those. Converting from rectangle to polar.
I thought we went from Cartesian to polar.
What'd I say?
Rectangle.
Yeah, Cartesian and rectangle, they're the same.
Okay.
Okay, let's do 2 and 4. X equals 2, y equals 4. What should we do?
And this is from just Cartesian to polar again, you said?
Yep, Cartesian to polar.
Okay, so start with, because it starts with r comma theta,
Mm-hmm.
but to get, well, I guess you could start with either of them
Mm-hmm.
because of the Pythagorean.
Yep.
But yeah, I'll just do it in order. So I'll start with the Pythagorean, and so it's 4 plus 16, so it's 20. So that's going to be 2 root of 5. All right, and then for the y value, it's 4 over 2, and that's just 2. And so after that, you have to do the arctangent of 2, which I'm not sure what it is without a calculator,
Yep.
but that one's pretty simple with a calculator.
Yep. Yeah, expect if you're doing these on a exam, without a calculator, that it'll be a unit circle value.
Mm-hmm.
Um,
Hopefully, fingers crossed.
yeah, fingers crossed. If not, you'll just leave it as this. You leave it in terms of arctangent. So we would say that our answer is 2 square root of 5, arctangent of 2. And that would be our answer.
All right.
Okay. Yeah, so I like to think about these problems, or these equations in kind of two groups.
Mm-hmm.
Yeah, so this one I used to go from polar to rectangle, and this one rectangle to polar.
Got it.
Okay, so that is for points. Oh yeah, that's converting between rectangle and polar and rectangle for points. It's a little different when we're talking about functions. So let's say we had, ooh, this will be a fun one. Let's say we have y is equal to 3x plus 2. We want this in polar coordinates. What should we do?
Okay. So you have, so you need to find the x and y intercept, right? Or is that not how that works?
So it's already in um, slope-intercept form, but that's not going to help us. Even if it wasn't in slope-intercept form, we'd still be able to convert it to polar. So right now we have y and x. We don't want y and x. We want r and theta.
Okay, so just swap them out.
Sure, how should I swap them out?
Y being, should you put r sine of theta or just theta?
R sine of theta.
Okay, the full equation, yeah. And x being r cosine of theta.
Yep, 3r cosine of theta. Plus 2. Plus 2 is fine. Okay. And here's the thing you need to know about these kinds of polar problems. In the same way that in Cartesian coordinates, we solve for y, is equal to x and stuff, we solve for r is equal to theta and stuff. So we need to solve for r. So how do we do that?
So you have to get r by itself then.
Mm-hmm.
So I guess you would divide it out of here.
I'll say no, because if you divide, so one, if you divide by r, you have to do it to everything.
Mm-hmm. And that
Oops.
wouldn't get it by itself then,
Yeah.
because it would be underneath the 2.
Yeah.
Got it.
And so it's not because it would be alone, because it would be the only r, but it's in the denominator, and we want it to be in the numerator. And what that would mean is we would have to eventually multiply it back out, and then we just kind of undid what we just did. So we
Okay.
could save ourselves a step. Do you have any other ideas as to how we could get r on its own?
Subtract this thing over to the other side.
Very good.
Like the entire thing.
Yep, the entire thing. So we're going to have r sine theta minus 3r cosine is equal to 2. Now what's next?
I'm guessing you're not supposed to divide the 3 out, are you?
We don't have to.
Oh, because it comes division,
Mm-hmm.
which makes it tangent.
Maybe.
Wait, no.
So how do we get these r's by themselves?
So it becomes division. So it'd be, it would just divide to 1/3, right? Or would you need to separate it? So you could do a GCF, I guess.
Yeah, that's what I'm looking for. So we pull the r out, and we get sine of theta minus 3 cosine of theta. And now r is on its own, and we just have this, thing attached to it. So how do we get rid of that thing attached to it?
I guess you could just divide it to the other side.
Yep, that is exactly right.
It seems really messy, but I mean, it's a valid solution.
Yep, it is valid. So the reason it's messy is because polar coordinates are not good at lines, straight lines.
Mm-hmm.
They're very good at curves, and you'll see that if we were to take an equation that's very easy for polar and turn it into Cartesian, it looks really gross in Cartesian. So that's why we use these different forms. It's because for different things they're useful. And I want to show you why. So I'm going to share Desmos with you. So we had y is equal to 3x plus 2. This is a normal line, so we expect. Desmos allows us to graph in polar if we have r. So if we say r is equal to 3x, or it would be, wait, hold on, it would be r is equal to 2 over sine of theta, theta, you'll see that it produces a straight line.
Huh. Okay.
So it works. It just looks weird.
Mm-hmm. So you need to like overcomplicate it to simplify, which
Yeah.
seems.
And it's just the nature of polar coordinates. It's very easy to do circles. It's very easy to do these other kinds of weird circles. It's very easy to do all these kinds of weird looking curve things. Very easy. But this would be like almost impossible to do in Cartesian. In fact, we might not even be able to do it because it's not a valid function.
Yeah, I was gonna say it doesn't pass the vertical line test, so I don't think so.
Yeah. So this is why we use polar. We can write things that we can't write in Cartesian. Okay. So that is that problem. Let's do one more conversion one. Ooh. Okay, this time we're going from polar to Cartesian. I think this one will be cool. This one might be a pain in the ass, but we'll see. So we have r is equal to 3 over 1 minus 2 cosine of theta.
All right. So, which way were we going? Did you say?
We're going polar to Cartesian.
Okay. Okay.
Yeah. These ones are kind of tricky, so I don't blame you.
I'm trying to even figure out like. I guess you could do. The r is the x plus y.
Mm-hmm.
Like you could change that out. Or the x squared plus y squared.
Yeah, let's do that. So we have square root of x squared plus y squared of theta.
Mm-hmm. And then to get the theta out, you would have to use tangent?
Kind of. So the thing is, we don't have y and x. So like if we had y divided by x, yeah, we could. Or if we had just tangent of theta, then we could throw in y of our x. But we have cosine. So
Okay.
what I think we're gonna have to do is use this one. and then have it be x over r is equal to cosine theta, and then we can convert r into x squared plus y squared.
Oh, ew.
Yeah.
That's
very,
just
very apt description for it. Ew.
that's awful. Okay, so like you said, you'd divide the r over to, the x. So it'd be x over r is equal to cosine theta, and then you'd have to make it, yeah, that's that
That's
one's
something.
very awful.
Yeah. So we're not done though. We'll do our damnedest to try and solve for y. I don't think we'll be able to, or well, actually we might be able to. We'll see. So, what do you think we should do?
Logic would think that you're supposed to use this equation, but I'm not sure how that helps us much, because I thought you were supposed to keep the theta kind of like out of the equation.
Yeah. No, once we don't want our theta.
Yeah,
We have x and y's now, so we don't want to do any more converting.
that's what I was thinking, but
Yeah, now we're just doing algebra because we're trying to solve for y.
We're
trying to see if that's possible.
Can you separate them, like the square roots?
What do you mean separate them?
Like square root of x plus, square root of x squared plus square root of y squared.
Nope.
Okay.
Can't. That won't work.
Can you not just get rid of the square root start?
What do you mean?
Because they're both squared. So does that cancel out the square root?
So the formula is r squared equals x squared plus y squared, but this is just 1r, and this is just 1r over here.
Okay. So the only thing I can think of, because we're getting, you said x on its own?
We're trying. We're just trying.
Y.
Y. Just normal.
So
normal stuff.
And you can't divide it over because they're adding, right?
We can multiply this over. We just have to multiply it by everything.
Okay.
So 1 minus 2x over. So this is square root of x squared plus y squared times. I'm just going to copy this over.
Okay. And then at that point,
what happens?
You can. I'm guessing you wouldn't want to distribute.
You do.
Of course.
No, it's okay. So the reason I see distributing is because this is gonna cancel here. You see that?
Yeah.
So we're gonna end up with square root of x squared plus y squared minus 2x equals 3. Then I want to get rid of the square root, so we have x to the y. So I'm going to is equal to 2x plus 3. Square both sides. So x squared plus y squared equals, I'll just say 2x plus 3 squared.
And then you can just subtract the x squared over.
Yep. So we're going to get y squared equals 2x plus 3 squared minus x squared.
And can you just take the square root of both sides, or?
You can.
Just to make it cleaner.
So we get plus minus 2x plus 3 squared minus x squared. So theoretically, we can reduce the inside here because this is, we're going to have an x squared term, an x, just a normal number term, and then we might be able to do something here. but we can stop.
Thank you. That was awful.
Yeah, no, yeah. So this is kind of what I mean, where like certain equations are really good in certain forms, certain
Mm-hmm.
curves, and if we actually, let me share my screen with you.
And this one should not be in Cartesian.
Yeah,
That's for sure.
yeah. So this is what it looks like. This is
Wow.
called a hyperbolic function. So it's like parabola but hyper,
Yeah.
and that's you won't have to worry about this kind of curve for a long time. But it's a cool little thing. I think it's hyperbolic. It looks hyperbolic at least, but that's besides the point.
Hopefully, I don't have to see it again.
Okay, so when did you want to finish up today? Because I thought you said you might want to leave early.
Yeah, probably at like 45 minutes or 50, something like that.
Okay, so we got about
Either like 3:20,
5 to 10 minutes
3:25.
left.
Yeah.
Okay. Um, have you talked about complex numbers at all in polar coordinates?
No,
Okay, we won't talk about that then.
we haven't even really started it because we spent the entire day really doing the FRQ.
Oh, okay. You know what? Let's be done with math. Um, I want to show you some uh kind of like important forms of Cartesian coord of a polar form. So, kind of the first thing we're introduced to is just r is equal to a number.
Okay.
And it's just this function is just wherever the radius is 5, we plot a point. So we end
Mm-hmm.
up with a circle. This is also true for -5, because if you think about it, if
The radius is still 5, yeah.
yeah, instead of starting over on this 5, we maybe start on this 5. Doesn't really change much. The next kind of common forms is if we have a number times a trig function. Oh wait, I need to be in theta. There we go. So it's still a circle, but it kind of moves it off to the side.
Okay.
And so that's for cosine. If we do it for sine, it raises it. So you see the same idea.
Oh, so it starts from the kind of like the center makes it like the unit circle, right? Because it goes all around -1, 1, 1, and 1.
Um, so that's just because of the coefficient I chose. If I chose
2. Okay, so
1,
it would
it'd
be.
be different.
Oh, got it.
So like if I chose 6, it's bigger.
Mm-hmm.
It's just what I happen to pick. But like they shift between cosine and sine. They rotate 90 degrees, which is what we expect because cosine of x and sine of x are the same function but shifted over 90, not minus 90, plus, wait, not plus pi over 2. I'm in radians. I always forget. But cosine and sine are the same function basically, just shifted over.
Mm-hmm.
Okay, so that's one kind of graph. The other is if we add, oh, not theta. There we go.
It looks like a brain.
Yeah, and actually, so we want and this will change depending on how big the numbers are relative to each other.
Okay, and so if you were to add a slider, you could like see how it changes.
Yeah. Okay. And if these numbers are the same, we get it where it gets down to like a point right here.
Hmm.
And how, whether if it's plus or minus, that'll rotate it. So that'll rotate it around.
Okay.
If it's sine, it'll rotate it 90 degrees.
Got it.
And then that'll flip again. Yep, but then we have the brain one where it's if they're bigger, like that. Then we have the one where there's a loop inside. If we have it squared, is equal to 4 cosine of theta. It doesn't like it. It won't graph it because it's r squared. Let's see if I this, and then we would need the minus version. There we go. So imagine these are all one thing.
Okay.
We can kind of get
it'd be plus or minus, yeah. Okay.
we can kind of get like a figure 8 thing going. And now this one is my favorite. So if we have r is equal to a number, cosine of theta, but now we increase the period.
Huh.
And so if it's even, it'll be like that. If it's odd, it'll be like that. And then we can keep going up.
Yeah, I actually use this equation because we had to do like a Desmos art thing where we like made pictures, and I use this for a Christmas present, like the bow.
Yeah, good choice. Good choice.
Had to Google that.
This one's also pretty cool. Is if it's r is equal to theta, we get a spiral.
Oh, okay. So it's just got it.
Yeah, and it kind of makes sense because as you get close farther around the circle, theta is greater, so the radius will also be greater. And yeah, these are all the kind of basic polar graphs, and they got all these funky names. Rose curves, Limacon. I actually don't know if it's set, how the C is pronounced, but yeah.
Okay.
And then it also has the general forms. I don't know if you'll need to know these. I didn't, but after you do enough problems, you kind of like recognize the patterns.
All right.
Okay, and it's good to know the general shape of graphs anyways, because
Mm-hmm.
If you want to graph a parabola, you kind of need to know what a parabola looks like. But yeah, I think we're good. We can cut a little bit early.
All right. Thank you.
Yeah, thank you. I'll see you next time.